This is Algebra 2, Unit 8, Lesson 7, and we're talking about the type and number of roots of a polynomial function and end behavior of a polynomial function. And so first we're just going to review. The roots of a polynomial expression or equation are the same thing as x-intercepts, solutions, or zeros. So the x-intercept have four different names: roots, solutions, zeros, and x-intercepts. And that basically means where the function crosses the x-axis. There are several different types of roots, and we've talked about these before. A real root is a root that visibly crosses the x-axis. So you might have an xy coordinate system, and then you've got some sort of polynomial function graphed. And in this polynomial function, this crosses the x-axis at three distinct points. We could use Desmos to find out exactly where those points are if we had an equation for this. So that's what the function would look like. And it doesn't necessarily have to have two curves. It could be a parabola crossing at two different places. It really doesn't matter how many curves it has or how many times it crosses. It has real roots when it visibly crosses the x-axis. If you have a double root, this is something that we've talked about. This is where the maximum or minimum point touches the actual x-axis. So you see in these, the maximum point here is above the x-axis, the minimum point here is below the x-axis, and here as well, it's below the x-axis. But we will have a double root if we have something like this. We've got an xy chart, and then let's say we have a function that does something like this. Well, if you look at that function, it's got a real root right here, but right here, see where this minimum point is actually touching the x-axis? That is something called a double root. So let's just say that that happened at the number 2. That means we would have a double root at 2. So x minus 2 and x minus 2 would be two of the factors of the polynomial equation that this will produce. Let's say this one, I'll just say that that's at -2. So the third root, or the third factor there, would be at x plus 2. Remember, the factors, if the roots here are x equals 2 and x equals 2 and x equals -2, their roots for this one would be x plus 2. For this one would be x minus 2. And for this one would be x minus 2. So you see that y would equal this equation. For the third one, an imaginary root, that's when you have your maximum or minimum point somewhere and it doesn't cross the x-axis. For example, we might have something like this. If that happens, this minimum point never allows the function to cross the x-axis. So this would have two roots, because this would be a polynomial equation with 2 degrees, and it has two roots that are imaginary because this thing never crosses or never touches the x-axis. You might have something like this, where it crosses at one place, but then that minimum never allows it to touch the x-axis again. And so in that one, we would have one real root right here where it crosses, and two imaginary roots at the minimum that never crosses it. So we've talked about all three of these before. That's just a recap on the type and number, well, the type of roots that you could possibly have. We're identifying the number and type of roots given a graph. Okay, so let's say we have this graph. Okay, well, we can see that right here at -2 and right here at 2, we have two real roots. Now, how do you tell the degree of a polynomial equation? Well, that's really easy. To figure out the degree, it will equal one more than the number of curves in your graph. So if they just give you a graph like this, what you can do to figure out how many or what the degree is, you can count how many curves it has. All right, so look here. This has got one curve here, two curves, 3 curves. This thing has 3 curves, so that means the degree is 4. It's a 4th degree polynomial. So if our degree represents the number of roots this function will have, well, it has to have 4 roots. If it has 4 roots, we know 2 of them, one of them is -2, another one is 2. So that accounts for 2 of the roots. So one of the roots is -2, another root is 2, and then looking right here, this is a maximum that doesn't allow the polynomial function to cross the x-axis. So this is where we would end up with 2 imaginary roots. So we have -2 is a real root, 2 is a real root, and then we have 2 imaginary roots that we don't know what they are. We would have to be given an equation for this to be able to figure out what they are. Now I want you to notice something here. This comes in later. If this is a degree of 4, the degree is an even degree. That's an even number. Notice both of these functions on the end, the left end and the right end, they're both going up. That's going to become significant in just a little bit. Okay, when we're talking about the end behavior, what we're looking at is what's happening on both ends of the polynomial graph. So we're talking about what's happening to the y's. Are they going up or are they going down as x approaches the left and as x approaches the right? So when we're writing end behavior, if the directions say find the end behavior of the polynomial function or find the end behavior of the function, here's how we will always start the end behavior. We will start with as x approaches -infinity, y approaches, and then we'll figure out whether it's going up or down. If it's going up, it would be approaching infinity. If it's going down, we would be approaching -infinity. The second part of end behavior, you would write as x approaches infinity, y approaches blank, either infinity or -infinity, depending on whether it's pointing up or down. So we always start out the same way. This right here, as x approaches -infinity, means as x moves left, y moves either up or down. If y is going in an upward direction, we would put infinity. If y is going in a downward direction, we would put -infinity. This means as x moves right, y approaches. If it approaches an upward direction, we would put infinity. If it approaches a downward direction, we would put -infinity. It's pretty simple. So if I go back to this one and we talk about the end behavior, well, let's look at the end behavior on the left side and on the right side. I would write this as x approaches -infinity, as x moves left, as x moves left. So what's happening on the left side? Well, on the left side, y is approaching, it's going up, so it's approaching infinity. Let's look at the right side. As x approaches +infinity, as x moves right, y approaches, well, that's going up as well. So that also approaches +infinity. So end behavior is determined by 2 things. It's determined by the degree of the polynomial, and it's determined by the sign of the leading coefficient. So we don't necessarily have to have a graph to be able to find the end behavior of a function. And when we're talking about the degree of the polynomial, and we'll do examples of this in a few minutes, if the degree of the polynomial is even, it's an even degree, then for the end behavior, they are both going in the same direction. So what that means is if it's an even degree, you might have a function that does this. That's an even degreed function because it has 1, 2, 3 curves. That's a degree of 4. They're both going up. It might look like this. That is a 1, 2, 3, 4. That's got 5 curves. So that's a 6th degree function. They're both going down. So to do the end behavior for this, let's look at this one first. As x approaches -infinity, as x moves left, y approaches infinity. As x approaches infinity, as x moves right, y approaches infinity. It's going up. For this one, as x approaches -infinity, y approaches -infinity. As x approaches infinity, y approaches -infinity. So if the degree is even, both of these will go in the same direction. If the degree is odd, then the ends go in opposite directions. So let's think about that. Let's draw one that has opposite directions. There's one. Look at that one. It has 1, 2 curves. So that means its degree is 3. That's an odd degree. They're going in opposite directions. One's going down, one's going up. Let's look at another one. Thinking about how many curves this one has. It's got 1, 2, 3, 4 curves. So the degree is 5. In an odd degree function, they will go in opposite directions. So for this one, as x moves left, y is going down. As x moves right, y is going up. So this one would be as x approaches negative infinity, y approaches negative infinity. As x approaches infinity, y approaches infinity. For this one, as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches negative infinity. Now, how do we know whether they're going to be going in the same or opposite directions when we don't have the graph? Well, that's really simple. That has to do with the leading coefficient. In an even function, so if the function is even, meaning its degree is 2, 4, 6, 8, 10, and so on. If the degree is even and the leading coefficient is positive, that means they're both going up. So it would be going up on both ends. So that's this situation. If we have an even degree and the leading coefficient is negative, then they will both be going down. That's this situation. If the degree is odd and the leading coefficient is positive, then you can think about that like a positive slope. That means it will be going in this direction. In other words, the left will be going down, the right will be going up. We have this situation when that happens. That would be in the direction of a positive slope. If the degree is odd and the leading coefficient is negative, then that means it's going in the direction of a negative slope. This one, a negative slope, remember, is this direction. This one is the one we would be talking about, negative slope. So let's do some more examples. So if we're finding the end behavior given a graph, there's a bunch of stuff we can figure out by this. Let's say I give you, and I'm not going to ask you for specific roots, I'm just going to ask you for the end behavior and the type of roots that this has. Now, if I look at this, I know for this function, I've got 1, 2, 3 curves. So that means for this function, my degree is 4 because it's 1 more than the number of curves. So that means I know I'm going to have 4 roots. All right, let's talk about the type of roots that has. Well, it crosses the x-axis visibly there, right here, and right here. So to me, it looks like that's going to cross the x-axis at 4 distinct points. So those 4 roots are going to be real roots. No imaginary roots in that. Let's talk about the end behavior. Well, looking at the left, and remember, we start end behavior the same way. As x approaches negative infinity, y approaches something. And as x approaches infinity, y approaches something. And we have to figure out what those two somethings are. Well, as x approaches the left, as x moves left, y is going down. So y approaches negative infinity. For this part, as x approaches to the right or moves right, y is again going down. So y approaches negative infinity. There's my end behavior. So there's a lot we can tell by this graph just by looking at the direction of it, looking at how many curves it has, and so on. Now, if that was a proper graph, I would be able to tell where those roots are on the x-axis. But I just did a real simple little graph there. For this one, well, if we look at that, think about it. What is the degree of that function? Well, it's got 1, 2 curves. If it has 2 curves, then the degree is 3. That's an odd degree. If it's an odd degree, the 2 ends are going in opposite directions. Which part or which direction is this going? Well, the leading coefficient here, we could distinguish, is the leading coefficient positive or negative? Well, if you think about the direction of this, that's going up toward the left, down toward the right, so that's telling me it's kind of a negative slope direction. So the leading coefficient here would have to be negative. If I ask you to find the roots here, it's crossing the x-axis, it looks like at 1 and at 2, and then over here at -4. So the roots are -4, 1, and 2. If it asks me to write a makeshift equation for this, well, f of x, my y value, is equal to, and all I have to do is turn these roots into factors. The factor that goes along with this is x plus 4. The factor that goes along with the 1 is x minus 1. And the factor that goes along with the 2 is x minus 2. So that I could consider the equation. That's supposed to be an equal sign. So this could be an equation for my polynomial graph. I do not have to multiply all these together for this to be a function. I could take this and put it into Desmos, and it should graph something very similar to this. So it doesn't have to be real difficult when we're just writing kind of a simple equation for what this possibly could represent. One thing we also need to understand here is if we were to FOIL all three of these, wouldn't the first term be positive? So since we know this is in a negative direction, we would need to put a negative, either a -1 or some kind of a negative coefficient in front to signify that this one is moving in a negative slope direction. For the end behavior of this one, well, we started out the same way. As x approaches negative infinity, y approaches, and then as x approaches infinity, y approaches. Okay, as x moves left, y is going up. So y is approaching infinity. As x moves right, y is going down. So y is approaching negative infinity. So there is my end behavior. So you see there's a lot of things we can do and a lot of things we can figure out by finding the graph or using the graph of a polynomial equation. This one's just asking us for end behavior. So that's all we're going to find here. For the end behavior, it looks like it's going down to the left and down to the right. So there's a lot I can tell about this. I know the degree must be even because they're going in the same direction. They're both going down, so I know the leading coefficient must be negative because they're both going down. For the end behavior, I started out the same way every time. As x approaches negative infinity, y approaches. And as x approaches infinity, y approaches. Okay, as x moves left, y is going down. So that's approaching negative infinity. As x approaches the right, as x moves right, y also approaches negative infinity. That is my end behavior for that function. That has one curve. Degree was 2. The two roots are -3 and 5. So there's a lot we can tell by a function like this. If they were to ask us to find an equation for that, well, I could say y equals, if this root is -3, the factor would be x plus 3. If this root is 5, the factor would be x minus 5. I know it's going down. If I FOILed this, my leading coefficient would be positive. I know it has to be negative because they're both going down. So I would just stick a negative number in front. What that negative number is in front really isn't important at this point. We just need to understand that it would be negative. Let's talk about relative maximum and minimum points. We've talked about that a little bit already. If there are relative maximum and minimums, they're not going to be necessarily the lowest point on the entire graph, but they're points where the direction is changing. So right here, that would be a minimum. This would also be a minimum. And they're relative minimums because if you look, everything below 0 is actually lower than these two. But our relative minimums tell us where the direction changes. For our relative maximums, we have one right here. We have one right here. We have two relative maximums. You know those are not the maximums because we have some points on that graph that go in the upward direction that are bigger than those two. They're relative because that's where our direction is changing. So remember back when we talked about where is this function increasing and decreasing? We could say that this function is decreasing from negative infinity until we get to -1. It's decreasing, I'm going to say from about 0 until we get to 1. And it's decreasing again from wherever this point is till the x is infinity. So from whatever this point is until infinity. We could say it's increasing from -1 to about 0 and from 1 to wherever this point is. So our increasing and decreasing is based off of the x values. Our end behavior is based on the direction x is moving. So if we're talking about end behavior of this graph, x approaches negative infinity as y approaches infinity, and x approaches infinity as y approaches negative infinity. So looking at this one, would it be even or odd degreed? I'm going to say it's odd because they go in different directions. And would the sign, the leading coefficient, be positive or negative? Well, it looks to me like that's going in a negative direction, so it would be negative. Could I ask what the degree of this function is? 1, 2, 3, 4 curves tells me the degree is 5. So there's a lot that a graph will tell us, and that is one of the big topics in Algebra 2, is understanding how to analyze graphs and what they're telling you. So let's put it all together for this one. So this is the exact same graph, okay? So putting it all together, what is the degree? Well, it's got 1, 2, 3, 4 curves, so the degree is 5. The leading coefficient, this is going in a negative slope direction, so it would be negative. For the end behavior, we've done this already, but as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches negative infinity. State the number and types of roots and state the roots that you can find. Okay, well, if it's a 5-degree polynomial, it should have 5 roots. So let's talk about which ones are real. Well, it crosses the x-axis here, and since that minimum is actually on the x-axis, that tells me that's a double root. So I have 2 roots at -1. I also have a double root at 1, and I also have a root at 2. Now, in Delta Math, when they ask you for the roots, they're only going to want you to name them -1, 1, and 2. They do not want you to distinguish the double roots. They don't want you to write that twice, and that's okay. You just need to understand that -1, -1, 1, and 2 are the roots, and you need to understand why -1 and 1 are double roots, even though you don't have to necessarily state that every single time you're just naming the roots. And then another thing they might ask you to do is to write a little makeshift equation for this. Well, if I make these roots into their factors, okay? If -1 is a root, the factor for -1 would be x plus 1. Now remember, I had 2 of those, so I'd use x plus 1 again. If a root is 1, its factor would be x minus 1. And remember, I have 2 of those, x minus 1 again. If my root is 2, the factor for that would be x minus 2. I could say that that equals f of x or y, and then I need to account for this being in the negative direction. So I need to understand that it does have a coefficient in front, and that coefficient has to be negative. Now, I don't know whether the coefficient is a whole number or a fraction, but I do know it has to be negative. So they may give you choices, and they may say, which of these functions could possibly be the function for the graphed equation? And as long as it has a negative in front and it has these 5 factors, that would be a choice that would be right. So let's talk about how to find end behavior when they give us an equation instead of when they give us the graph. First thing you have to do is make sure the equation is in descending order. If you don't, then your leading coefficient won't be in front, and that may confuse you. So make sure that your polynomial is in descending order. Finding end behavior is going to depend on 2 things: the degree of the polynomial. If it's an even degree, we know they're going to be going in the same direction. If it's an odd degree, they're going to be going in opposite direction. If the sign of the leading coefficient is positive or negative, that will help us determine how to write the end behavior. So if the leading coefficient is positive and you have an even degree, then they will be both up. If the leading coefficient is positive and it's an odd degree, then they're going in opposite directions, but it would be in the direction of a positive slope. So down toward the left, up toward the right. If the leading coefficient is negative and the degree is even, then they would both be going down. If our leading coefficient is negative and the degree is odd, then your function will be going in the direction of a negative slope, up toward the left down toward the right. So let's write the end behavior of these equations. All right, first thing I'm going to do is it written in descending order, x to the fourth, then x squared, and then x to the 0. So yes, it is. End behavior always starts out the same way. As x approaches negative infinity, y approaches something. As x approaches infinity, y approaches something. So let's talk about what y is approaching. Here, this degree is even. So we know they're both going in the same direction. The leading coefficient is positive. So if they're going in the same direction and the leading coefficient is positive, that means they're both going up. So in both directions, y will be approaching infinity. Look at the second one. Is it in descending order? No, it is not. I need to write it in descending order. So negative 2x cubed plus 4x squared minus 8x plus 2. Here, my degree is odd. That tells me they're going in opposite directions. Here, my leading coefficient is negative. So that tells me it's going in the direction of a negative slope. So we started out the same way. As x approaches negative infinity, y approaches. And as x approaches infinity, y approaches. As x approaches negative infinity, as x moves left, y is going up. So it's approaching infinity. As x moves right, y is going down. It approaches negative infinity. It is that simple. It's very simple to find end behavior of equations as well as graphs. For this one, it is written in descending order. It's an odd degree. That tells me they're going in opposite directions. It's a positive leading coefficient. That tells me it's going in the direction of a positive slope. We started out the same way. As x approaches negative infinity, y approaches. As x approaches infinity, y approaches. All right, looking at this one. As x moves left, y is going down. As x moves right, y is going up. For this one, it is written in descending order. It looks my degree is even. Looks like my leading coefficient is negative. So I'm going to start it out the same way. As x approaches negative infinity, y approaches. And as x approaches infinity, y approaches. So as x moves left, now looking at this one, it's an even degree, 6. If it's got a 6th degree, it means it has to have 5 curves. And if the leading coefficient is negative, they're both going down. So if we think about that, it's got to be going down from the left. Has to have 5 curves. 1, 2, 3, 4, 5. The function will look something like this. That's how many curves it will have. Now, we don't know how high the maximums or low the minimums will be, but that's just a basic shape of what the graph will look like. So, as x approaches negative infinity, y is going down, so it approaches negative infinity. As x approaches infinity, y is again going down, so it approaches negative infinity. So let's write some polynomial equations for these functions. They're both going up. I know this is an even degree function. The degree is 2. It looks like it's got a double root at x equals negative 2. So if x equals negative 2 are the two roots, then my two factors would be x plus 2 and x plus 2. I'm going to say y or f of x equals that. They're both going up. So I do not need a coefficient in front. I just need to understand that it is a positive in front. That would be my makeshift polynomial equation for this graph. It may not be exact because it may need a number in front, but as long as we know that number would be positive, that's all we need at this point. For this one is it's got 2 curves, so it's a 3-degree function, so we should have 3 roots. If we're looking at that, the roots, we've got 1 at 0. We've got 2 roots at 2. So that means for the x equals 2, my factors would be x minus 2 times x minus 2. Well, that's twice, or that's 2 of those, so I'm going to just square it. Then if x equals 0, well, technically, wouldn't that be either x minus 0 or x plus 0? So that's just a factor of x. So we need the x in front. This one is going in a positive direction, so we know there's a number in front that's positive. We don't know what that number is, and I'm just going to set that one equal to f of x. Again, you could use y instead of f of x. Doesn't matter a bit. So that's a look at the degree, the type of function, and the end behavior of graphs.